Hello, from now, I will talk about the physical origin of H mode. This voice is AI, but my name is Lee from Korea Institute of Fusion Energy. Here is the contents. After the introduction of fusion research, and what is the H mode, I will show how three equations are developed. First is the zero-center shift current equation, second is the turbulence diffusion equation, and the third is the Reynolds number equation. Using these equations, the physical origin of H mode will be explained. The physical origin of H mode is the most important unsolved problem in the plasma physics. If you search internet for the list of unsolved problems in physics, for example, here in Wikipedia, number 1 unsolved problem in plasma physics is what is the physical origin of H mode, which is regarded as on the same level as is it possible to produce energy for nuclear fusion? Then, why is H mode so important? Here is a brief history of fusion research. Manhattan Project produced the first atomic bomb in 1945. 6 years later, Enrico Fermi developed the first fission reactor. The first hydrogen bomb using fission and fusion energy was made in 1953, leading people to believe that a fusion reactor would be within a decade. Project Matterhorn was a plan for the peaceful use of fusion energy and was developed at Princeton University's Plasma Physics Laboratory. Since the fusion reaction requires more than 100 million degrees of temperature to contain such hot plasma, it uses the helical motion of charged particles in a magnetic field. Plasma particles spiral and become trapped in the magnetic field, and if the magnetic field is shaped like a donut, it can only spin and move within it. Such a torus-shaped plasma confinement device is a tokamak. But that's where physics encounters an unexpected obstacle. The magnetic field cannot completely trap the plasma, as particles trapped in the inner magnetic field and particles trapped in the outer magnetic field can change their positions when they collide, and a small amount of plasma can escape the magnetic field from a higher density to a lower density, which, according to classical physics, is inversely proportional to the square of the magnetic field, so it should rapidly decrease when a strong magnetic field is applied. However, in the experiments, it is found that the plasma leaking is only inversely proportional to the first power of the magnetic field, and the amount of escape is more than 100 times larger than the expected value. This phenomenon was proportional to Bohm diffusion equation, which was also discovered by experiment, so its physical origin was uncertain. This unexplained diffusion phenomenon called anomalous transport had to be studied. And the cause of this anomalous diffusion was turbulence. While 30 years passed far from the success of nuclear fusion. Then came the good news from the German fusion device Aztecs. H mode has been discovered, which is the suppression of turbulence. H mode means high confinement mode in contrast to low confinement mode. Transition between them is called L to H transition. When H mode transition happens, the turbulence measured as density fluctuation delta N over N, suppressed, so the particle leaking drops rapidly, and the density and temperature increase. H mode makes the plasma pressure and confinement time doubled, so it gave a hope for nuclear fusion. Since the first discovery, H modes have taken place at almost every tokamak of the world, and their experimental feature is known. First, H mode is triggered by increase of heating power, so it has power threshold. In H mode, turbulence is suppressed at the edge. Power threshold increases with B field. Power threshold is inversely proportional to ion mass, so-called isotopes effect. H mode do not occur well when there are too many impurities. Power threshold is high when the plasma density or too high, so it has U-shaped dependency. H mode occurs when right amount of neutral atoms are inserted. H mode are more likely occur in diverter plasma than limiter plasma. The power threshold is lower when ion grad B drift is toward the X point than away from the X point. LH transition has bifurcation, hysteresis. The radial electric field near the boundary increases after the LH transition. ER profile plays an important role in LH transition. The LH transition takes place in a short time, about 30 to 100 microseconds. H mode seems random in its approach, sometimes occurring and sometimes not. H mode is most often followed by an edge localized mode, which recurs periodically. H mode has been researched for 42 years. Numerous researchers published numerous papers on the origin of H mode, but it remained as unsolved. So far, theories are denied as Feynman's famous quote, "It doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong." Therefore, the real answer for H mode origin must explain these 15 experimental characteristics. To explain the LH transition mechanism, we need to know how a current is formed at the tokamak edge. And this came from the charge exchange reactions. Before the reaction ion and gyromotion encounters a neutral, here an electron of the neutral switches its ride to the ion, so the ion becomes a neutral and the neutral becomes a new ion starting a new gyromotion, so the center of gyromotion shifts from here to there. The gyrocenter shift for electrons is very small compared to ions due to the mass difference. This happens only for ions, and when there is one directional movement, it generates a current. So gyrocenter shift current requires either one direction of the neutral, which is the case of the ionosphere, or one directional movement of ions, which is the case of the tokamak edge. Charge exchange reactions take place at the relatively narrow region at the edge, since further inside there is no neutral, and further outside there is no plasma. The momentum change by the charge exchange reactions is a force that is in equilibrium with the J cross B force. Here the B field is in the toroidal direction and the momentum change is in the poloidal direction, so the current is in the radial direction. The relative velocity between the ions and neutrals, which contributes to the momentum change, has at least 4 components. The first is the diamagnetic drift, which comes from the higher plasma pressure on the left side than the right side to make a downward motion. The second is a similar term that comes from the neutral density gradient. Higher neutral density on right side than left side generates a net downward drift. This term is a new one. Then there is the ion grad B drift when the B field on the left side is higher, so the gyro radius changes large and small to make a net downward motion. Finally, when there is a radial electric field, ions get acceleration and deceleration to make an upward motion, which is E cross B drift. The driving terms of GCS current are pressure gradient and density gradient, so they are not uniform. Here it is small, here large and small, so after gyrocenter shifts, charge separation takes place. The current generates charge by continuity equation, and charge generates E field, so iteration of these 3 equations forms the radial electric field, which compensates initial driving terms. Then, the current becomes 0 and the equilibrium is reached. Typical formation time is about 30 microseconds, and here is a key rule for GCS current: it always puts ions from the plasma side to the outside. Now we switch the topic to turbulence. Our goal is to understand how turbulence is generated and suppressed, but before this, we need to understand how turbulence induces diffusion. This textbook figure shows the diffusion of early fusion devices follows kT over EB, so-called Bohm diffusion, although this front constant is not always matched. And in 1980s European tokamak found that the diffusion is proportional to the square of turbulence magnitude. US tokamak found the turbulence is only high at the very edge of the plasma where the plasma and neutrals are mixed. When we look closely at the vortices generated by the turbulence at the plasma-neutral mixing region, we will see a structure in which the plasma-rich and neutral-rich regions, the plasma particles are trapped by the magnetic field, but the neutrals are not affected by the magnetic field, so the turbulence moves them around, creating a denser mass of neutrals than the surrounding plasma. The GCS current always pushes ions from the plasma to the neutral side, so that positive charges are collected on the neutrals and negative charges are collected on the plasma. This phenomenon is microscopic. The resulting E cross B drift velocity then creates a circularly shaped convection, in which both ions and electrons are in circular convection across the magnetic field. Since the plasma density on the left side of the figure is higher than on the right side, this circular convection causes diffusion of the plasma, and the amount of diffusion in one revolution of A to B and to C, here, can be calculated as the derivative of the plasma density multiplied by the distance traveled in one revolution, which must be multiplied by the ratio delta N over N, since not all plasma particles undergo this circular convection, but only the plasma component that participates. To calculate the flow rate from this diffusion, E cross B circular convection speed is multiplied to the amount of diffusion, then this is the diffusion coefficient. Since delta R times E field fluctuation is the potential perturbation, it can be replaced with this by the Boltzmann relation. Now we have the turbulence-induced diffusion coefficient that explains both experimental observations, kT over EB, and square of fluctuation. Here if delta N over N is 0.3, it becomes the Bohm diffusion, but this is just a coincidence. Another important point is that this diffusion is also applied to the charge separated by GCS current. Now we can talk about how turbulence is generated and suppressed. This the Reynolds number, which is the ratio of inertia force to the viscosity force when there is a friction. This number distinguishes turbulent or laminar flow. If this number is higher than critical value, it will be turbulent. It is lower, it will be laminar flow, like the flow of water from a faucet. The transition from turbulent to laminar flow in H mode can be characterized by the Reynolds number for the friction between the plasma and neutrals when the plasma moves as a fluid under the influence of electromagnetic forces while the neutrals are not affected by electromagnetic forces. However, the Reynolds number between plasma and neutrals under a magnetic field differs from that of a typical neutral fluid in at least 3 ways. First, the object causing the friction is a solid, such as a water pipe in the case of tap water, but in the case of tokamaks, it is the neutrals, so it must be defined from an individual particle perspective. The second, dimension of scale, such as the diameter of a water pipe, is reduced to the zero-radius of an ion in a tokamak. This is because, for a given neutral, an ion that is further away than the zero-radius in the direction perpendicular to the magnetic field cannot collide with that neutral. So the Reynolds number becomes like this. This is mean free path of ion-neutral collision, this is ion zero-radius, and this is ion thermal velocity. The third is that the rate at which the fluid experiences friction, the relative velocity of the ions and neutrals, is determined by the equilibrium conditions that arise in the interaction with turbulence. When there is turbulence, equilibrium condition will change. Although GCS current tries to separate charge, this turbulence-induced diffusion make a return current to hinder the charge separation. So the new condition for the steady state is this equation. Since GCS current includes this velocity term using these two equations, this velocity term can be replaced with other parameters, then the final Reynolds number becomes like this, and this one equation can explain the physical origin of the H mode. At the boundary of a tokamak, there are neutrals which are largely not moving, and the plasma particles moving in poloidal direction due to the electromagnetic force. So between them, there is a friction. In the beginning, plasma density and temperature are low, so the Reynolds number is high enough to be as turbulent state. In this L mode, plasma particles leak from inside, strike the wall, and make a recombination of ions and electrons to become neutrals. This is called recycling, which supply more neutrals around this diverter region. Then as heating is increased and temperature increased, Reynolds number becomes smaller than the critical value to suppress the turbulence. This is the LH transition. Upon the transition, Reynolds number becomes even more smaller since this turbulence term is reduced, then the laminar flow region can extend to inside of the boundary separatrix. And this region becomes the transport barrier. Let's explain all 15 characteristics by this equation. First, as H mode is triggered as ion temperature increases, there is a threshold for the heating power. Second, this Reynolds number explains the turbulence suppression. Third, power threshold is proportional to the B field due to this term in the numerator. Number 4, power threshold is inversely proportional to ion mass due to this term in the denominator. Number 5. For impurities, since they have many electrons, the charge exchange is not effective for the momentum exchange, so when there are too many impurities, the main ion density becomes small and Reynolds number is high, so H mode do not occur well. Number 6. Power threshold has U-shaped dependency on plasma density is relatively new discovery. I got this equation in 2009, at that time I didn't know about the jet result, and all the other observations of U-shaped dependency were after this equation, so if this equation can explain the U-shaped dependency, it will be an experimental verification of the equation. U-shaped dependency is that the LH power threshold is high when the plasma density is small, and it becomes high again when the plasma density is too high. Reynolds number has plasma density in the denominator, so left side of U-shape is agreed but right side looks not matched. However, there is a hidden parameter, which is neutral density. To increase plasma density, we put more neutrals as fuel, so it seems to opposite to the Reynolds number equation at first glance, but the increase of neutral occurs only outside of plasma. Inside, it decreases as plasma increases. The governing equations of plasma and neutral have a common term of ionization as source for one and sink for the other. So these coupled differential equations have solutions as hyperbolic functions as introduced in a textbook. As plasma increases, neutral decreases since the penetration length reduced. This analytic solutions were experimentally agreed at D3D tokamak, here, low plasma density with high neutral density, and high plasma density with low neutral density. Now we know that as plasma density increases, the neutral density decreases inside plasma although neutral increases at outside. Here as plasma density increases from A to B and C, neutral density decreases as values at middle point. All the combinations of two parameters plasma density and neutral density are compared with experimental data for the power threshold. While other combinations do not match, this 1 over Ni times square of Nn is remarkably agreed with the observation. And this is exactly the same in the Reynolds number formula. So U-shaped dependency came from that when Ni is too low, Reynolds number is high to be as turbulence, power threshold is high, and when Ni is too high, then the square of Nn is too low to make power threshold high again although plasma density is high. We continue 15 characteristics of H mode. Number 7. When right amount of neutrals are inserted, high neutral density triggers H mode. Number 8. For a diverter plasma, recycling takes place at this confined space so neutral density increase effectively, but for limiter plasma recycling takes place open space around limiter, so it is difficult to trigger H mode. Number 9. Ion grad B drift is a part of ion velocity which transfers to neutral velocity by charge exchange reactions. When ion grad B drift is toward X point, neutrals are pushed to this confined space to increase neutral density to make H mode easier. Number 10. H mode occurs when the Reynolds number reduces to critical value. Once transition happens, Reynolds number reduces even more by this turbulence is reduced, so once transition occurs it won't go back as it came, which is a hysteresis. Number 11. After the LH transition, turbulence-induced return current is no longer valid, so GCS current keeps continue to separate charge and increases radial electric field. Number 12. ER profile plays an important role in LH transition. This is because the Reynolds number formula includes the second gradient of ER, so even when other parameters make Reynolds number high, turbulence can be suppressed where the ER has inflection point with this term close to zero. In the TFTR tokamak, when the ER profile has inflection point, a transport barrier took place at that point. And for the EPH mode of NSTX, the inflection point of ER is exactly matched with transport barrier. Number 13. The time constant of this iteration for the ER formation is typically few tens of microseconds, so LH transition occurs in such a short time. Number 14. There are parameters in the Reynolds number formula, which are not measured routinely such as neutral density, and sometimes impurities, turbulence magnitude and error are not well measured, so with only measured parameters, H mode seems random in its approach, sometimes occurring and sometimes not. Number 15. The H mode is most often followed by an edge localized mode, which recurs periodically. The mechanism of ELM is a serious research subject to be discussed separately, but, briefly, the laminar region of H mode is more vulnerable to MHD instabilities, especially when E cross B flow is matched with effective rational surface, then ELM crashes, then it goes back to H mode to rebuild the condition including radial electric field and certain amount of time to repeat it. Before going to the conclusion, I'd like to tell that there are additional findings. If GCS current is real, it should be found elsewhere than tokamak. The reverse rotation against Lorenz's direction of the cathode spot in the cylindrical arc discharge was first discovered by Stark in 1903 and remained unsolved for 104 years. In the famous textbook written in 1991, said no satisfactory explanation of this effect has been found, even at the qualitative level despite numerous attempts. This is explained by the reversed E field induced by the GCS current in front of cathode spot in 2007. So now a new textbook includes this explanation for the reverse rotation. There are other additional findings using these two equations. The origin of Bohm diffusion was explained in 2015. The E-field formations in Earth's ionosphere, including the equatorial electrojet and black aurora, were explained in 2017. The origin of intrinsic rotation on tokamaks, which was unsolved for 20 years, was explained 2023. And all of these explanations were possible since the quasi-neutrality is violated. When charge exchange reactions generated point charges, if this ratio is greater than unity, all the space becomes inside of Debye shielding, so E-field formation is possible. And this ratio was indeed larger than 1 for all applications. Here is conclusion. The physical origin of H mode is explained using this one formula of Reynolds number, induced by these three equations. All 15 characteristics of the H mode are agreed, including U-shaped density dependency and favorable ion grad B drift. Now we can control turbulence suppression using this equation at a broader region in the tokamak, so density and temperature will increase as well as confinement time, which means nuclear fusion is possible. Thank you for your attention.